let us know more about photodiode by studying its IV characteristics and variation of photocurrent as a function of reverse voltage and intensity. Photodiode terminals are identified as the longer lead is identified as a positive terminal and the smaller lead is identified as the negative terminal. This photodiode is invented by John N. Shive, an American physicist, in the year 1948. It is basically a PN junction operated under reverse bias and prepared to take up advantage of its internal photoelectric process. When the junction is illuminated, the electron hole pairs are created in the depletion region, which provides an incident photon energy to the charge carriers in the junction whenever the photon energy is greater than the energy gap of the semiconductor. The semiconductor used in photodiode may be silicon or germanium. The photodiode actually consists of a simple PN junction diode which is embedded in a glass or clear plastic socket. The upper surface of the photodiode is open so that the radiation can be incidented upon it, and the other part of this diode is enclosed in metallic case. The magnitude of photocurrent generated through the junction depends on the level of illumination. There are two types of photodiodes, point contact type and junction type. When there is no illumination, the photodiode acts as normal junction diode. These photodiodes are used in alarm circuits and counter circuits, which has got numerous applications in the field of engineering as well as in public service. The procedure for the study of IV characteristic as well as the variation of photocurrent with respect to the applied reverse voltage can be done in two parts. In the first part, we study the IV characteristics of the diode. So, the diode setup is placed in such a way, the photodiode is placed in line with the LED which emits light, so that the light falls directly onto the photodiode. So, this is the setup required so that we can study the characteristics of photodiode. So, in turn the LED is connected to the power supply, wherein you can vary the illumination of the LED, and photodiode is connected in the circuit in reverse bias. In series with milliammeter, connect a voltmeter across the photodiode. So, we have a built-in power supply in this kit. So, connect the power supply. Let us do the experiment. The experimental setup requires the experimental kit, LED with variation of illumination power, a photodiode. So, photodiode and LED is placed in face to face so that light falls directly onto the photodiode. The photodiode, let us start the first part of the experiment where we study the IV characteristics of the photodiode. for which the photodiode should be connected in reverse bias condition, because the photodiode works in the reverse bias condition when it is illuminated. Let us see how exactly it works. So, we have inbuilt power supply in the kit. So, we will connect that first. The diode is inserted in the socket so that it is placed in reverse biased mode. Connect a microammeter in series with the photodiode to measure the photocurrent flowing through the circuit, and connect a DC voltmeter across the photodiode to vary the voltage across the diode. Now switch on the power supply. Cover the setup of alignment of LED and photodiode with the cover so that no other lights interferes. Now you see that the diode is connected in reverse bias. For any variation of voltage across the diode, the current flowing through the circuit is showing 0 from the meter. Now switch on the LED power supply. You see that LED is on now. You find a flow of current through the diode, hence it is registered on the micrometer reading. So vary the voltage in steps of 0.1 and record the corresponding microammeter readings. Tabulate them. Keeping the illumination at 10 milliwatts. Repeat the experiment with another level of illumination, say 20 milliwatts. You observe that the current through the junction is increasing for the same set of variation of voltages. Record the corresponding readings and tabulate them. Plot the characteristics. We observe that there is a variation of current only when the illumination is there on the photodiode. But when the illumination is off, since the diode is connected in reverse bias, you observe a very small flow of current through the diode, which is called as dark current here. It is because of the reverse saturation current through the diode. So which can be shown through the using multimeter, because it is very small current. I can show you a small current flowing when the illumination is off. A very small current for the variation of voltage of the order of 0.3 microamps. Very small, and it remains almost constant, 0.3 or 0.4 microamps, very small current called dark current when the illumination is off. So no illumination, so the corresponding current is referred as reverse current called dark current here in photodiode. Now let us move on to the second part of the experiment, wherein we study the variation of photocurrent with respect to illumination. So now the illumination is off, switch on, set say around 1 volt reverse bias across the junction, constant, keep it constant, and vary the illumination power. So, now the power of LED is 10 milliwatts. You see that current is around minus 460 microamps. Now, vary in steps of 1, 11, 12, 13, 14. You observe that the current is increasing linearly. So, as and when the illumination is increasing, you observe that photocurrent is increasing. So, readings are tabulated and graphical observation says that the photocurrent produced is directly proportional to the applied illuminated power, not on the applied reverse voltage across the diode. The related Viva questions are listed